This lesson is an extension of the previous lesson on logarithmic functions, but this time we'll look at some transformations. So it really doesn't introduce anything new, but it does give us another long look at transformed graphs. So it's really practice for Unit 1, and it also gives us a chance to work more with logarithmic functions and get more comfortable with them. So I'm going to launch right into these. Describe and sketch the following. So number 1, y is equal to the log of x minus 2 base 3. So it's a logarithmic function with a base of 3, telling us that it is an increasing logarithmic graph. Remember, if the base is bigger than 1, that will be the case. We should note the transformations, and there is a horizontal translation of 2 units right, courtesy of that x minus 2. So we're taking our standard function, log of x base 3, looking like this. Notice that we have that x-intercept of 1. And we now just pick it up and move it 2 units over to the right. Simple as that. So the graph in red then is our transformed function. The x-intercept is 3. Makes sense, just 2 over. The domain, you do get domain and range questions with these a lot, so you got to be right on top of them. The domain is going to be x greater than 2. Now, this can either be done by inspection, but be careful. I've got a dotted line in indicating the new asymptote. And really it just amounts to the fact that the y-axis originally was the vertical asymptote, but it too has been moved 2 units over. So therefore the new asymptote is going to be x equal 2. Now the other way is algebraically you can take this x, the function, which is y is equal to the log of x minus 2 base 3, and concern yourself only with this x minus 2, because for a logarithmic function we do know that the number we're taking the log of has to be greater than 0. So we just go x minus 2 greater than 0, so therefore x is greater than 2. Both methods work. Don't rely overly on your calculator because you'll have to trace and then be very, very careful. And by inspection, you may not be able to pick it up. If you draw it by hand, however, you probably will get it. But the algebra will always, always work. The range will be simple because for all logarithmic functions, the range is always all real numbers. Let's try another one. Y is equal to the log of x base 4 plus 3. So another increasing logarithmic graph, but here we have this vertical translation of 3 units up. So if we take a look at the untransformed graph, y is equal to the log of x base 4, looks like this, x-intercept of 1. We just pick this up and move it 3 units up, looking like that. So this point, which previously was 1, 0, will go up 3 units, so it's going to be 1, 3, and that's verified by inspection of the graph as well. Now, with respect to the domain, I'll just draw the transformed curve. That has no effect on the domain. Because there's no horizontal stretch or anything, it's still going to be x is greater than 0, all real numbers. And the range is also unaffected because just moving it up doesn't affect anything. It still goes to infinity in both directions. So y is an element of the set of real numbers. Take a look at another one. Here we have f at x is equal to 2 log of x base 5. Another increasing function, but we do have that factor of 2 being multiplied into the log graph. And this will tell us that we have a vertical stretch by a factor of 2 about the x-axis. So, if we take a look at the untransformed curve, looking like this, base 5, notice this one's a little bit flatter than the previous ones, which we would expect if we have a base of 5. And our vertical stretch will then stretch the graph away from the x-axis, giving us this. And every y-coordinate has been doubled, although we don't have many to work with. Notice the x-intercept is unaffected because that's 1, 0 would not change. But that's this point, for example, which is 5, 1 on the original, will transform to 5, 2 on this one, which makes sense for us. Domain and range, not expecting an awful lot of change. The domain, still greater than 0, XER. We haven't done anything horizontally, so the domain will not change. The range also, the fact that we're stretching it vertically isn't going to make it not go to infinity in both directions. So y is an element of the set of real numbers. Let's try another one. Here we have y is equal to the log of negative x to the base of 1/2. So for the first time today, we have a base that's less than 1, which tells us that it is going to be a decreasing function. Also, the negative x, the replacement of x with negative x, produces a reflection in the y-axis. So here is our untransformed graph. Y is equal to the log of x to the base of 1/2. X-intercept is still 1, but it is decreasing. So we just simply reflect that in the y-axis, and we get y is equal to the log of negative x base 1/2, looking like that. Interestingly, with your domain, by inspection, you can probably identify this as being x is less than 0, XER. This could also be found algebraically if you wanted by setting negative x greater than 0, as just setting whatever you have there greater than 0. And remember, when you divide by a negative, you might remember that that has the effect of reversing the inequality. You may not have seen that for a while, but that's that old trick when dividing by negative. So x is less than 0. Range, you'll see no change. So the range is going to be all real numbers, just as it always is for logarithmic functions. Let's take a look at another one. The last one, f at x is equal to the log base 2 of 5 minus x. Now this is written in kind of an unconventional form. So what I would advise everybody to do first off, as we did with previous functions or transformations, to get it into an identifiable, recognizable form, we want that x to not have a coefficient with it. This one is basically written backwards. So take out a factor of -1. And of course, dividing by -1 will make the x positive, and dividing by -1 from 5 will turn that into x minus 5. So we get this. And now we have two transformations to consider. We have the reflection in the y-axis, and then we also have a horizontal translation of 5 units, right? So you might remember that you need to take out a factor of negative or whatever coefficient or multiplier is with the x term in order to identify the horizontal translation better. Now, here is our untransformed curve. Y is equal to the log of x base 2. So I'm just going to walk it through those two transformations. We reflect it in the y-axis like that. And then we take that curve and we translate it 5 units over to the right. So we can see our x-intercept is 4. So we just can follow it. As long as there's no vertical translations, we just follow it. Now what's interesting is our domain, not so much our range. So when we go after the domain, you may be able to tell by inspection that x is less than 5, XER. And we could see that I did draw the dotted line in for that. But if you can't tell, do the same thing. I'll actually do that in the next step, but we'll do it algebraically, and we can solve for it like that. Always we can. And then the range is all real numbers. So let's take a look at the algebra behind the domain again. We have f at x is equal to the log of 5 minus x base 2. Now you could take whichever form you want, but the key idea is that for y is equal to the log of x base b, x must be greater than 0. Must be. So for this 5 minus x, we simply note that 5 minus x must be greater than 0. Negative x, if you isolate that, is greater than negative 5. And then through division, when you divide by a negative, you must reverse the inequality, and then you get x is less than 5. It will always work. Many times, if not all the times, you can tell by inspection of the graph, but this is a very reliable method too. So that'll take care of this exercise. The next one, we step away from graphs and get into the algebra. Thank you for your time.